And now we'll begin the second presentation on equilibrium. All right, let's take a look at the Haber process. Haber process is a common equation used when we look at equilibrium because it was the process that enabled Le Chatelier to understand equilibrium better and figure out how to make fertilizers from it. Since it's such an important equation, it becomes the most important equation that we use in the discussion of equilibrium. So we see it's an endothermic process. We're given our equilibrium concentrations, so we've allowed our system to reach equilibrium, and these are the concentrations of the ammonia, the nitrogen, and the hydrogen gas. And so the questions are, what's the value for K? Is the forward reaction favored? How can we increase the amount of the product? Okay, so we go and plug our concentrations in. We figure out the K value from using those concentrations. So we're treating all of these as elementary equations, so therefore the coefficients will be the superscript numbers in the equilibrium expression. So we're not worried about mechanisms here, even though the equilibrium is coming from the rates. So we have hydrogen cubed times the concentration of nitrogen divided by the concentration of the ammonia squared. So we plug in the concentrations that we were given for equilibrium into the expression, and we find out that our K value is 2.6 times 10 to the negative fifth, which means that this is not a reaction that's favored. Since the exponent is to the negative power, it means that we have a fraction in our expression that's significantly less than 1, and therefore the reactant is more likely to be present at equilibrium than the products are. The product can be increased by increasing the temperature. Since it's an endothermic reaction, that will shift it to the right. Decreasing the pressure because there are more moles of gas on the left side than there is the right. Increasing the amount of ammonia will shift it to the right, or removing hydrogen or nitrogen. So all of those things are used to create the ammonia when the Haber process is being used on the industrial scale. All right, so now we can look at another way to focus on equilibrium is to see, well, what if we're not at equilibrium and we know what the concentrations are and we also know what the K value of the expression is? What does this tell us about where we currently are now? Which way does the reaction have to shift in order to reach equilibrium? So it's possible to measure the concentrations of the reactants and products in the reaction vessel at any time. They might not be at equilibrium, but of course they also might be. So when you plug those into the law of mass action or the equilibrium expression, you will still get a value, but it might not be the K value. So what we do is we say it's the reaction quotient, and we call it the Q value. And we can take that Q value and compare it to K, and then we can see which direction a reaction is favored to move. Is it going to be a forward reaction favored in the near future or a reverse reaction favored in the near future in order to reach equilibrium? So let's look at the Haber process again. And we see that we have those concentrations. So if we plug them into the equilibrium expression, we find that our value for Q is 1.3 times 10 to the negative seventh, which is very, very far away from the K value for these conditions. So since Q is significantly higher than the K value, then the concentrations of the products needs to decrease to get closer to the K value, and the reactants concentrations need to go up, meaning that the reaction will shift to the left in order to reach equilibrium. So just simply throw the concentrations in, calculate the Q value, compare the Q value with the K value. If the Q needs to decrease in value, that means less products, more reactants, shift left. If the Q value needs to increase in order to reach the K value, then that would mean more products and less reactants, which means it's going to shift to the right. All right, so we don't always have simple expressions. Sometimes we have situations where we have mixed phases or mixed substances, so we call this heterogeneous equilibria. And the way we can solve this is by using ICE problems, and the ICE stands for initial concentration, change in concentration, equilibrium concentration. So it's based on the stoichiometry, and then we can use this to determine the concentrations once equilibrium is reached if we know the starting concentrations and the K value. So here's an ICE problem. For the reaction carbon monoxide plus water yields carbon dioxide and hydrogen, we find out that the K value is 5.10. So we want to calculate the equilibrium concentrations if the initial concentrations of all the components is 1 molar. So we start with 1 molar for all of them. We know based on the stoichiometry that for each mole that carbon dioxide is produced and hydrogen is produced, that we will also have 1 mole of carbon monoxide removed and water removed. So that's why the change is minus X for the reactants and plus X for the products. If the stoichiometry wasn't all 1-to-1, then we would just have 2's and 3's in front of the X's depending on what the coefficient was. So our equilibrium concentration then for the carbon monoxide and the water is they both started at 1 molar, and we're subtracting X amount, so it's 1 molar minus X. And then for the carbon dioxide and hydrogen, since we started at 1 molar, we're adding that amount, so it's 1 molar plus X. So we plug that all into the law of mass action, and we solve for X, and we find out that X is 0.387. So what happened was everything was a square there, so we took the square root of both sides and then solved for X. So that's how we got X to be 0.387, which means that for carbon monoxide and water, we started with 1 molar and we subtracted 0.387 from both of them, so what's left is 0.613 molar. And for the carbon dioxide and hydrogen, we added 0.387 to each one, so their final concentration will be 1.387. If we have a situation where we don't know what that X value is and it's going to make the problem more complicated, what we can do sometimes is say, okay, if the K is so small and the concentration of the substance is large, then as the reaction occurs, there will be very little change in the concentration. So then we can drop X at that point from the change in the reactants, which makes the problem easier to solve. So let's look at this example. We have 2 NOCLs going to 2 NOs plus Cl2. The K is 1.6 times 10 to the negative 5, and so we want to know what the equilibrium concentration will be if 1 mole of NOCl is added to an empty 2-liter flask. So we know that we're starting with 1 mole in a 2-liter flask, or 0.5 molar, so always make sure that you convert your moles into concentration or this won't work. So we start with 0.5 molar NOCl, but we don't have any nitrogen monoxide or chlorine to start the reaction. So as the NOCl gets used up, the change will be minus 2 times X, and for the NO, it's going to be plus 2X, and for the chlorine, it's only going to be plus 1X because of the coefficients from the balanced equation. So our concentration at equilibrium is going to be 0.5 minus 2X for the NOCl, but for the NO and the Cl2, it's going to be plus 2X and plus X. So we plug that into our expression with the K value, and we get 1.6 times 10 to the negative 5 equals 2X, that whole thing squared, because of what the expression says, the concentration of NO needs to be squared, times X, divided by 0.5 minus 2X, that whole thing squared. So this is going to be a very difficult thing to work with. We're going to have cubes and all sorts of things, so it's going to be very difficult to solve algebraically. But since K is to the negative 5 power, and the starting concentration is 4 powers of 10 greater, then we can ignore the change in our reactant concentration. So we can take out the minus 2X from the 0.5. So our new expression becomes 1.6 times 10 to the negative 5 equals 4X cubed over 0.5 squared. So we square that, multiply it through, divide by 4, take the cube root, and we get that X equals 1 times 10 to the minus 2. And we go back and check, as long as the change in concentration is smaller than 5%, it's valid to ignore it in this class. You don't have to worry about doing the algebra then. So plugging the change into the law of mass action and demonstrating that the K hasn't changed is another way to prove it. So you can either check and see if the change is 5% of the original, or you can plug it back in and show that it's not going to change your answer. And so the final concentrations of the NOCl is still 0.5 molar because it was such a small change, but for the nitrogen monoxide it's going to be 2 times 10 to the minus 2 molar, and for the chlorine it's going to be 1 times 10 to the minus 2 molar. So that's all the other things that you need to know about equilibrium. I know this one was a little shorter, but this is probably one that you're going to want to watch a couple times just to make sure you get all these nuances, because they're going to be very, very important as you go through the next chapters.